Okay, now let's talk about why it is a good idea to use the J error, the J cost function that we are using, which is the sum of the squares of the subtractions of the model and the real value of y. And we are going to analyze this from a probabilistic point of view. So suppose that we have a training example I, and we can write that this output of the example I can be computed, as we saw before, as the dot product of a vector of parameters and the input vector of variables for that example. So here we are assuming that we can compute this output as a linear combination of the input variables. And let's assume also that this product contains some error, some epsilon. And assume that this error, so each example will have some error. Suppose that this error can be drawn from a normal distribution with mean 0 and variance sigma square. Okay. So if we assume that this error can be drawn from a normal distribution, we can write then that the probability of some error to have some value can be expressed like this. This is simply the formula of the normal distribution. Okay, so we are saying that the probability of an error can be computed with this expression. Now, we have said that this error appears in this expression, and we can solve this equation for epsilon. So if we move this term to the left, then we will have that epsilon equals y minus the dot product of theta and x. And that expression is exactly the one that we are going to write here instead of epsilon in the next step. So now instead of having the epsilon here, we have y equals the dot product of theta and x. Okay, and we can say then that the probability of getting some y, given that the input vector is some x and that we have some parameters theta, can be estimated using this probability distribution. Now here, in terms of the notation, you see here a semicolon here. That means that whatever it comes after this will be parameters of our probability distribution. So in this case, x and y are variables, random variables, and theta is a vector of parameters. Okay. Now we can write the likelihood of theta. So the likelihood is simply a function that has as argument the parameters of a probability distribution. So we said that our parameters here are theta. So we can write the likelihood of our data set as the L of theta, which turns to be the probability of y given x with parameters theta. Now, given the independence assumption on the epsilons, we can also write the likelihood like this. So here we are assuming that each of the errors in our model are independent from each other. Okay, and if that is true, then we can define the likelihood or write the likelihood as the product for every example that we have available, for every endpoint, as the product of y given x with our parameters theta. Okay. And we said before that we are assuming a Gaussian distribution, a normal distribution, and we can simply replace this expression of the probability with the formula of the normal distribution. Now, given a set of points, these m points, what we want to do is to find the parameters that will allow the normal distribution to fit as much as possible the data. So we are looking for the parameters theta that explain the best possible way the observations that we have, so the data that we have. So this is called maximizing the likelihood, or maximum likelihood. Now, to compute the maximum of the function likelihood, let me go back again, the maximum of this, we need to compute the partial derivatives of this expression. But we have a problem here, that we have too many products. So suppose that you have 1 million points. This is a product involving 1 million points, 1 million expressions. So this is very difficult when you want to compute the derivatives. So instead of computing the maximum directly to the likelihood function, we apply to this function the logarithm function, because the logarithm function is a function that is increasingly strict. So it means that it always increases, and that means that if you compute the maximum of the logarithm of this function, when you find the maximum is going to be exactly the same than if you compute directly the maximum to the likelihood function. So it is in this case it is equivalent, the maximization process, but it is easier because if we apply logarithms here, we can apply the rules of logarithm. And one of the rules of logarithms is that if you have the logarithms of the product of some variables, this logarithm is the same than if you compute the logarithms of the addition or the sum of these now terms. So we can transform this product here to a sum, and we can say that the sum of this for every point here up to the example m is simply the logarithm of the normal function. Okay, and this is much better because now we can compute the derivatives for each of the terms in our function. Now, if we factorize things here, like for example this denominator here, if we move it out and we move inside this sum here to apply directed to this subtraction, we get to this expression here. And here we have moved to the left as a factor all this expression here. And if you notice here, every element here is a number, is a scalar. So m is the number of points, we have the number pi, we have the standard deviation, sigma, and here sigma squared, the variance. And so you can imagine this like a simple scalar. And you see here what we wanted to see here in this development, which is that if we want to maximize this, the result of maximizing this, which this implies computing the partials of this with respect of every parameter and then equalizing that to 0, is exactly the same than if we minimize this. And this is what we minimized in the first place when we derived the stochastic gradient descent algorithm. So what we have shown here is that if you want to maximize, first of all, if you consider that each of the points can be generated in this way, like the dot product of a vector of parameters, or the linear combination of the inputs plus some error that is drawn from a normal distribution, if this is true, then to find the best parameters that explain our data, we need to maximize the likelihood, and maximizing the likelihood involves maximizing this expression. But maximizing this expression is the same, or you get the same result, the same theta vector, than if you minimize this, which is the one that we minimized initially. And this is a proof that shows you why this selection of the cost function is a good idea. So it is a probabilistic interpretation of this J function, this cost function. Okay, finally I would like to talk a bit about this locally weighted linear regression. This locally weighted linear regression is called a parametric method. This is called a parametric method because you need to save parameters in order to apply this. And in this case, what we are calling parameters are not the theta values, but we are calling parameters to all the examples or our data set that we have to estimate our linear regression model. And you will see why you need to keep those points. Here what you do is, if you want to evaluate one point, for example, you have a new house and you want to predict the price of that house. Suppose that this house is this X. What you need to do is to first of all minimize this expression with respect of the theta. And if you see here, you have exactly the J cost function, but with some with a change, slight change here, that is this W. This W is simply you can see it as a distance measurement of how close the point that you want to evaluate is to each of the points in your data set. So the idea is that in this minimization process, you will take more into account those examples in your data set that are closer to the point that you want to evaluate. So imagine again the example of the houses. This means that you will, in order to predict the price of a house, you will consider more important the prices of those houses that are more similar to the house that you want to evaluate. Okay, and you can have that result by using this weight parameter, and this is, as I said, is just a distance or a measure of similarity between the point that you want to evaluate and each of the points in your data set. So these parameters that you need to store are basically the points in your data set, because every time you want to evaluate a new point, you need to minimize this. Okay. One way to implement these non-negative value weights could be using the exponential. So in this formula, if xi is close to x, this is going to give you a large number. Okay, and if this difference is large, the exponential is going to give you a small number. Okay, so those houses that are more similar will have a larger W, and those that are less similar will have a small W. And this tau is simply a constant that you will need to find the optimal value for it that works well with your data. So graphically, what is this? Suppose that these are your points and you want to evaluate a point that is over here, this green point. Applying the locally weighted linear regression, what you are going to do is that all those points that are closer to this are considered similar, and then the model is going to adjust more to those points. Okay, so maybe the points here will be not very well predicted, and also the points over here, but we don't care about that because we are fine-tuning our model to those points that are more similar to the point that we want to predict. And if we were going to predict the value of this red point, again we will adjust our model more, considering the points closer to our red point, and maybe we'll get this straight line here. And we don't care about the prediction of this, and this, because they are far away from the point that we want to evaluate. So this locally weighted linear regression will get more precise, considering the points that are in the closer neighborhood of the point that we want to evaluate, whether it is this neighborhood or this neighborhood of another neighborhood. So that's it for this lecture, and talk to you later in the next lecture. Bye.